Okay, we are going to start out with Abel's theorem. Okay, here's the idea with Abel's theorem. If y1 and y2 are solutions to the following differential equation, y double prime plus p of x times y prime plus q of x times y equals 0. Bless you. Then the Wronskian of y1 and y2 is equal to c e to the negative integral p of x dx, where c is a constant that depends on y1 and y2, but not x. Okay, Abel's theorem gives us another way to calculate the Wronskian. Now, I would say that Abel's theorem is not particularly helpful because it only applies when you have two solutions and you have to have an equation in this form. So not the most helpful, but you still need to know it. What was the last example that we did? What number was it?
8.
8. Great. This is example 9 then. Okay, we are going to find the Wronskian of y1 of x is equal to x to the 1/2. y2 of x is equal to x to the negative first. If y1 and y2 are solutions to the following differential equation, 2x squared y double prime plus 3x y prime minus y equals 0, x being greater than 0. Okay, we're going to look at two different ways to calculate the Wronskian. First way, I'm just going to write before, or the old way, what we did yesterday. Or we could use Abel's theorem. We're going to do Abel's theorem, and then we'll review finding the Wronskian from yesterday. In order to use Abel's theorem, you need a lead coefficient of 1, which is not what we have currently. So let's get a lead coefficient of 1. When we do, we get y double prime, add 3 divided by the entire quantity 2x y prime minus 1 over 2x squared y equals 0. All we care about is that p of x, that's what's in front of the first derivative. So our Wronskian is going to be equal to c e to the negative integral of 3 over 2x dx, which is c times e to the negative 3/2 natural log of x. So we get c x to the negative 3 over 2. Okay. Now, here's one thing that is kind of interesting about Abel's theorem. This Wronskian is based solely on the differential equation. So any two solutions you have to this differential equation will have a Wronskian of this form. So it is more general. Are you ever going to need to use that? Is that ever helpful? In our class, no. So it's a fun fact that maybe you'll need in the future, but now you will not. Okay, I would like you to find the Wronskian now of these two using the determinant method from yesterday. Obviously, it should be some constant times x to the negative 3 over 2. Are we good if I give you the answer? Mm-hmm. Yeah, we're ready? You should have gotten negative 3 over 2, x to the negative 3 over 2. Do we want to see the work, or we're good for that? Yes, we're good, or yes, we want to see work? Good. Okay, great. I don't care what method you use. I think this is a better method, so I normally use this method. You do need to know Abel's theorem, though. For some reason, Eastern really likes Abel's theorem, so that's why you're learning it. Now, of course, we don't just get to use this theorem that I don't want to even use. We do get to prove it. Woo! This is our only proof for today, and it's not that bad. Okay. So we know that we have y1 and y2 that are solutions to this differential equation. So what I'm going to do is I'm going to plug both of those into here separately. So we get y1 double prime plus p of x times y1 prime plus q of x times y1 equals 0. And then same thing, y2 double prime plus p of x, y2 prime plus q of x times y2 equals 0. Now this is a system, so we're going to combine these. I'm going to multiply the top equation by negative y2, bottom equation by y1, and then I'm going to add them. Now, when you add them, it would be good to put them in the form that they're currently in. So something out in front, p of x times something, q of x times something. Okay, so we're going to have y1, y2 double prime. So y1, y2 double prime minus y1 double prime, y2 plus p of x times y1, y2 prime minus y1 prime, y2. And then you should see that these last terms are going to cancel each other out. So that term, they're the same. Okay. Side note before we go any further, we do need to use the Wronskian. So remember our Wronskian is y1, y1 prime, y2, y2 prime. Our Wronskian then ends up being y1, y2 prime minus y1 prime, y2. Which you should see is that right there. What we also need to know is what happens if we take the derivative of the Wronskian. I don't expect us to know this, but I'm going to ask anyway. Do we know how to take the derivative of a determinant? No, right? I don't see any reason you would have come by that. Okay, the way you take the derivative here is you take the derivative of one line, keep the other line the same, and then do it again with the other line. So I'm going to take the derivative of the first line, keep the second line the same. Then I take the derivative of the second line, but keep the first line the same. Okay. This, you should be able to tell, is just 0. So really the derivative of the Wronskian is this determinant right here, which you should notice if you find that determinant, it's this. So now if we go back to this equation we have, I'm going to star this. Okay, so what that equation becomes is we have the derivative of the Wronskian plus p of x times w equals 0. This is separable. So we're going to solve that by separation. dw over w is equal to negative p of x dx. So natural log of w is equal to negative the integral of p of x dx plus some constant c. So our Wronskian then ends up being c1 e to the negative integral of p of x dx. Okay, any questions on the Wronskian or Abel's theorem? Okay, like I said, Eastern loves Abel's theorem, so you're going to have to know Abel's theorem. So far, you now have 2 proofs that could be on a test. Isn't that exciting?
The first one, she already told me.
It's the first one? I told you it's the first one?
Yeah, I highlighted it, so you must have.
There is a large note next to my first one that says this one's on the
That's what
I'm pretty sure I didn't say that.
Star on.
Okay. I also told you, though, if you recall from earlier today, that I don't find Abel's theorem particularly useful, but that you have to learn it because Eastern wants you to learn it. Right?
Sir, I'm test.
Okay, we are still taking notes. That's not it for notes today. On a side note, though, in one of my classes, you know, from time to time, I like to give you all hints on what might be coming up. And I had a student like halfway through the year who still did not understand that. And he goes, "Are you telling us what's on the test?" I'm like, "Well, I'm giving you a pretty good hint right here." He goes, "Why do you do that?" I mean, I can stop. That's fine. Okay, last thing we need to talk about. Finally is non-homogeneous linear differential equations, which I called star 2 somewhere earlier in the notes, I think on day 1. Non-homogeneous just means that your differential equation is not equal to 0, it's equal to a function of x. Okay, one thing that we mentioned is we haven't solved any of these before, but if you are solving a non-homogeneous linear differential equation, you solve the homogeneous one first. So you always solve the homogeneous linear differential equation first, then solve the non-homogeneous one. Okay, quick note. Any function that we're going to call y sub p, which is free of arbitrary parameters, is called a particular solution. We've talked about that before. This just has some different notation. For example, if you have the differential equation y double prime plus 9y equals 27, so this would be non-homogeneous because it's equal to 27, not 0. One particular solution would be 3. You should be able to see that you can plug that in and it works. That's a particular solution. A solution to a non-homogeneous linear differential equation. We'll solve those eventually, not today. But what I need you to know is that all of the stuff we talked about is the same. And you're like, wow, that's not really helpful. Here's what I mean. You can still find the Wronskian. You still need linearly independent functions. You can still use the superposition principle. So all of those are going to be helpful in finding the solution. Only difference is the general solution. Okay, general solution for a non-homogeneous linear differential equation looks like the following. It starts out the same as the homogeneous solution, so C1y1 plus C2y2 all the way up to CKyk. Here's what differentiates it. You also have a particular solution at the end. So this is just the solution to the non-homogeneous linear differential equation, to the homogeneous one rather. So this is the solution to the homogeneous. When it's non-homogeneous, you get an extra particular solution at the end. Now, oftentimes it's not written like that because that is just a little tedious. So another way to write this is the following. That is the particular solution. All of that is written like that. This is called the complementary function. Complementary function or complementary solution. So for a non-homogeneous linear differential equation, you'll have a complementary solution and a particular solution, and you'll have to find both. Okay, this leads us to talking about the superposition principle again. This time it's the superposition principle for non-homogeneous linear differential equations. Okay. Let's say that you have y of p1, y of p2, all the way up to y of pk, and these are k particular solutions. Corresponding to g1 of x, g2 of x, all the way up to gk of x, of the linear differential equation that follows, g1 of x plus g2 of x plus gk of x. Then y of p, which equals y of p1 of x plus all the way up to y pk of x, is a particular solution to the linear differential equation. Okay. This notation is a little unclear. It's not the best notation. This is saying you have stuff on the left side. So this is all the normal stuff on the left side. So the a(n) of x times the nth derivative plus all the way down to a0 of x times y. This is the right side though. So instead of just having g of x, you have the sum of a bunch of different functions of x. So what you can do then for each function is find particular solutions, add them all together, which will give you one particular solution for the entire non-homogeneous linear differential equation. Now, remember, it is just a particular solution. It's not the only one. It just happens to be a solution. So let's look at how this is going to be used. Okay, I'm going to give you three particular solutions. The first one is negative 4x squared. The second one is equal to e to the 2x. And the third one is equal to x e to the x. And these are particular solutions to the following differential equations. So there's one particular solution for each differential equation. We have y double prime minus 3y prime plus 4y is equal to negative 16x squared plus 24x minus 8. Then we have y double prime minus 3y prime plus 4y is equal to 2e to the 2x. and then we have y double prime minus 3y prime plus 4y is equal to 2x e to the x minus e to the x. Okay, so this is a particular solution to the first equation, this is a particular solution to the second one, and then the third. Okay, so by the superposition principle, for particular solutions, which is what we wrote above, if we add all these together, we get the particular solution negative 4x squared plus e to the 2x plus x e to the x. This is a particular solution to the following differential equation. Left side is the same, so y double prime minus 3y prime plus 4y. Right side is the sum of all those g of x's, so adding all those together. Okay, here's how this is going to be helpful. Not this unit, but next unit. This unit is going to be all about how we're going to solve these differential equations, how do we find the particular solutions. Next unit, though, we're going to look at more applications. Left side is going to be the input for some function. We're going to be looking at motion mostly. And then the right is the output. So that's what we'll do next unit.